Hello, I'm Dr. Brian Fraser, and in this video I'm going to show how to use the fork command in Linux. So what is the fork command generally? It is a way of taking your currently running process and spawning a new process. And Linux has a rather unique way of doing this. It just duplicates the current process we're running. So let's walk through and see what we can do with that. So the first thing we might want to do is print out our process ID just to figure out kind of who we are. So we can do that with the get PID command in Linux. And so I'm going to do here, for example, just print it out. So printf I am and %d to show it as a decimal value. It's actually a type def, so I'm just going to cast it to an int to make sure it shows. And then I can build this. And it's going to say there's a problem because I haven't got the includes right yet. So if I move this up a little, it says implicit declaration of get PID. So anytime it tells you implicit declaration of something, C is telling you you haven't yet included the appropriate header files to include the command you're looking for. We can figure out what we should have included. I can go to a console. You can go Control Alt T if you're on a normal keyboard, and I can do man get PID. See if that comes up. Yep, that's what we wanted. And it tells us here that we should probably be including systypes and uni_std. So let's do that here. So hash include sys/types.h and hash include, and this is going to be uni_std.h. Now rebuild that, and it builds fine. So I can run this from the command line here, and that's my fork. Let me move that just on screen enough. And so there we see that I'm currently running as 10,929. And if I run this again, my PID keeps changing because, of course, I'm a new process to Linux. Okay, so let's bring in fork. What's fork going to do for us? So we're going to call the fork command. I can bring up the man page for that. Now when I just do man fork, it brings up the GNU AWK extension modules. That's not really what I wanted. Same sort of idea, but no, I want the programmer's reference. So I can do man2 fork. That'll force it to look in the Linux programmer's manual. And so here it tells us, well, it's in uni_std. Good, I've already included that. The fork command, we're going to pass in no arguments, and it returns to us a PID, a type def, which is the process ID. So I can say here, PID T, let's name it, say PID equals fork. So now when I run this, I'm not really going to see anything interesting happening. What I can do is I can duplicate that line here at the top, and I'm now going to make, oh, it's not going to like that because I have some warnings turned on. So let's put in here printf fork returned %d, and I'm going to type this, cast this. Okay. So now I'm just going to call fork. I'm going to print out whatever it returned, and I'm going to print out who I am at the end. So let's make that again. Let me just clear the screen so it gets. So I can call fork. Now we show off. Well, I start off being 11.017. Fork then says it returned 11.018, and fork returned 0. And then we see that we have an IM 11.017 and an IM 11.018. So what happened is we went into fork, just one of us, and we came out two of us, which is to say that the currently running process got duplicated. And this fork function returned twice, once in each process. And so my parent process came back, and it was the value that had this return. And my child process came back, and the child process came back with the 0. And in fact, that's how we know we're the child process when fork returns 0. So let's put that into some logic here. So if PID equals 0, now we know that we're the child, so printf, or child, printf I am the child, with PID, and I can't use the return value from fork because fork is going to tell me it's 0. That's how I know I'm the child. So I'm going to use int get PID. And I'll get rid of this line down here because I don't need it anymore. Now, if it comes back as a positive value, I can do else if PID is greater than 0, I am the parent. And if it's less than 0, it's an error. So often we put that at the front here, so I'm going to put it at the front here. If PID is less than 0, and let's put this in here, then I'm going to print an error. Fork failed. And you can look up the man page to figure out why fork will fail. It can fail if you're running, for example, a lot of forks. If you've got a process that's continuously forking new processes, you can run out of available processes with certain limits set by your restriction policy on your machine. Okay, so let's get rid of that. And now I'm going to move this up here so we can see exactly what fork returned, and then it'll tell us kind of who we are. So let me build that. And then let's run it again. So we start off as 090. Fork returns 091, and we therefore know that we are the parent. And then we're done. The other process comes back. Fork returned to 0. Therefore we know that I am the child, and my PID, when I look it up, is 91. So that's the very basics on getting that up and running. Let's do a little bit more here, though. So one thing that I'd often do is we are going to, so we got the error, we handle the error, so that's all on its own. Oftentimes inside this child area, I'm going to make it execute some code, and then I'm just going to call exit. So effectively, this is all the child is going to execute until it hits this exit command. This has the nice benefit of we can make everything after this, we must be the parent, because we've already handled the child and we've already handled the error case. So I know I'm the parent, and so then I can do whatever the parent should do. So we kind of isolate the code for fork to just this section here. So let me save and run that. And we're doing the same things before. Of course, the PIDs are changing. Okay, so let's demonstrate kind of this concurrency. The reason we'd spawn two processes, quite likely, is we want some more concurrency in our program. So let's make each of our child and our parent do something in the background. So I could do, for example, I could do a sleep command. It's sort of the very basics. I can sleep for, let's say, sleep for 5 seconds. Printf child exiting. And down here we could do some extra work, but as it turns out, one thing we're always going to, or very often going to want to do, is wait on our child process to terminate. It turns out there's good reasons to do this. We'll talk about those in a few minutes, but let's just put in the command that does that now. So I can put wait, and I'm going to put wait 0. This effectively, in fact, I want it to be wait null, a little clearer. This is going to wait until the child process terminates, and we'll handle that event here. So I am the parent, waiting for child to end. And I can put down here parent ending, because I'm now done. Rebuild that. The error, let's go to console, make, and it says implicit declaration of wait. Well, I can do the same trick I did before. Man wait tells me, oh, it's the wrong module. So I'm going to do wait 2, and it tells me that I should probably be hash including sys/wait as well. So I'm going to put that in here. Wait.h. There we go. We now build. So fork, and now we're waiting. So the child is running, the child then says it's exiting, and then the parent exited. So we do have that little bit of a wait. So what happened is the child began to run, it then waited, and then finally print out it is closing down. The parent was waiting for that to happen, and it then closed down as well. So that's just a little bit going on in the background. Let's do something a little bit more interesting. So let's, well, actually, before I go into that, let me just show you, if you're not using a make file, you can run I'll show you the actual command to build with fork. So the function that let's make clean, just to get rid of everything. So I'm building this fork file, so I can use GCC. I'm going to build fork.c. I'm going to output fork, and for this code, I'm going to use a for loop that has an embedded variable declaration. So I can use std equals c99. And for me, I always put on all warnings and turn warnings into errors. Let me just move that over a smidge. And so when I do that, it will then build my fork file. So that's the command I'm running via my make file, which is slightly more complicated but easier to use. Okay, so let's now go back and revisit the work that we're doing here. What I might want to do is, rather than putting a bunch of code for my child actually in my main, let's pull that out. So I'm going to make a function here. I'm going to call it do work. Do some work. And I'll get rid of that. So let's go up top here and write a do some work function. So void do some work. No arguments. Get the right style here. So what I'll do is I'm just going to go on through a loop and print out maybe a counter. Let's do that. So I'm going to create a counter. So const int num times, and let's go through, I don't know, 5 times. So for int I equals 0, I less than num times I plus plus. Now each time through, let's sleep, and I'm going to sleep kind of a random amount of time. So I'm going to do rand, and I don't want this to be a huge amount of time, so let's do rand, say 3, or 4. So that'll do a sleep between 0 and 3 seconds inclusive. So I'm going to sleep, and then I'm going to printf. This is going to say done pass. Let's put out the number I. Looks not bad. Compile that, and let's run it. So the child is now running. Done pass 0, done pass 1, 2, there's 3, and so forth. 4, and we're done. So we can do some work. I could do something very interesting, doing a lot of processing in the background. Sleep puts me off the run queue, so it's not a busy wait. So it's great for putting in timing. But if I had a lot of processor-intensive tasks, I could easily do it in this sort of function here. This is just a normal function that I simply am calling from my child process, or my child process. So let's see what's actually going on here. I'm going to bring up my other command line here, and we're going to use PS, which is going to show me the active processes. So I can use ps-a, and it'll list all of the processes that have been launched from this console. And if I go back up here and I rerun fork, it'll list here I've got these 2 fork executables. Now this is named fork because that's what I named my executable, but it'll list whatever it is you're actually running. And so we have exactly 2 of them. We really do have 2. I'll put a sleep here at the very front of my main. So after I put IAM, I'll put a sleep for, say, 5 seconds. Rebuild that. Rerun fork, rerun PS. We see we only have 1. I'm going to wait a second until we see the next output. We've now spawned 2, so I now have 2 of my forks. And then when it's all finished, it'll come back together with no forks, because they both terminate very quickly. So we can see that they both exist. The actual PIDs are shown here on the left. So we were 365, 368, as shown here, 365 and 368. The PIDs that Linux was assigning to us. Okay, so the next thing I want to show is sort of what does it mean to be a separate process. So far, we kind of have this idea that we're both pieces of code are executing in the same area. We've got the same kind of code base running. But what does it mean to be separate processes? So what I'm in fact going to do is I'm going to make this a global variable. I'm going to make I a global variable. So int I equals 0. And in fact, what I'll do is I'll even get out of there. So far, we're not really expecting any big change because only the client was executing this code. I'm going to go and I'm going to make the parent also execute this code. Now to differentiate the two of them, I'm going to make it parent. I'm going to pass in an extra argument here to each of my doWork functions, child. And so up here, doWork is now going to take a char star, and this is name. Done executing that pass for %s, and I'll put in the name here. Build that, we're all good. I can show you here the make. So, what are we trying to show? We're trying to show whether or not my two processes share a value. Each one is going to be editing this global variable named I, and so we'll see what should happen. If, for example, they're sharing the value, each one is going to be incrementing it, and so we'll expect to see this number go up quite quickly. On the other hand, if they're different, we'll see each, my parent and my child, get a full pass through 1 through 5. Let's try that. Oops. So we got pass 0 for both the parent and the child, all the way down. Now, I did this rand. We are actually both running in the same sort of pseudo-random sequence, so maybe what I'll do is, after fork, just add a little bit of rest. So I'm going to seed based on the PID. I think I want srand, in fact. There we go. So all I did is I'm just going to make it a bit more random. So fork. And so now they should wait for different amounts of time. Yeah, there we go. That looks better. So we can see that the parent counted up for 0, 1, 2, 3, 4, and the child got 0, 1, 2, 3, 4. So they're both completely separate values. So the global variable that is in each of the processes is completely different. We have two separate address spaces that don't interrelate. Anything I do in one address space does not affect the second address space unless I use special inter-process communication methods. Okay, so that's a little bit of work we're doing here. I'm going to go back, get rid of that global variable, because of course we all know global variables are evil. Int I equals 0, and we're back to some nice code. I'll let the parent and the child both still doing a bit of work there. That looked okay to me. We got the weight here. Now another thing that we can bring in is this whole return value from the child. Currently my child is returning 0, which is the success, the sort of standard value for success. But I could return a number of other values here too. So if I wanted to pass back or return a value of, say, 42, how do I get a hold of that inside of my parent process? Well, it comes through this wait command. So if I look at man wait, man to wait, this will tell us somewhere down here. The return value. Here we go. So on success, it returns the process ID that we're working with. So I can say, for example, which process finished. So let's do that. PID T child PID. So I'll put in here parent knows child %d finished, and I will pass in the PID. So int PID child PID. So if I run fork again, when this all finishes, it's going to tell me the PID of which child finished. Because I might have multiple children spawned with different calls to fork, and this will now show me which one of those has finished. So I know that it was 620 that finished, which was the only child I ever had here. Now what about the actual return value that I mentioned a moment ago, this exit 42, coming from the child process? Well, that's what this null is for. So what I can do is int status equals 0. This is expecting a pointer to an integer, so let's give it one. So let's give it the address of status. Now let's see what it comes back. Finished with status %d status. And we'll just see what that actually comes back as. Let that run for a second. It's going to turn out that the status isn't going to be quite as simple as you'd think. It's not just going to be that 42. It's going to have a bunch of other information encoded into the same value. So it came back with status, well, 10752. That looks a little weird. But what we can do is we can use a series of macros to interpret that. So what we can do is say int return, or let's say child return value equals, and I can use the macro w exit status, which I believe possibly stands for wait exit status, and I can pass in the variable I used here, which was status, and this will mask off only the portion of this status value that is going to be used for holding the return value, which is to say this 42. So let's print that out. So our return value was %d, and that was child return status. There you go. And just to make it format better, I'm going to put some spaces in front. So .fork. When it comes back, it's going to show us the return value that it's giving us back. There we go, the return value is 42. There's a sequence of, there's a large series of other macros here that you can use to find out was it a success or a failure, what terminated it, was it a signal, and so forth. So that's fairly powerful. Okay, so the second to last thing I want to show here is what happens if you don't use a wait statement. So this wait statement here. So what I'm going to do is I'm going to, before I do any work even on the parent, I'm going to do a sleep, and let's do a sleep 30. So I'm going to sleep for 30 seconds. And then I'm going to change this up here to just go through twice, make it faster. So what's going to happen is the child is going to end relatively quickly. It's going to take maybe, on average, kind of 4 to 6 seconds. And the parent is not going to have called the wait function yet. So it'll be sitting there sleeping, and then it'll come through and actually do the wait function. And what we're going to do is we're going to use ps-a to list all of the processes and see what's going on. So let's run that. So make fork. So I can use ps here, and we see that both forks are listed there as a 74 and a 75. Still there. Now the child has just finished. So note that the child, the 75, is now listed as defunct, which means the process has finished, but has not yet been waited on. So it is waiting to be waited on. This is known as a zombie process. It has to be kept around because it has that return value that we wanted. We couldn't just delete the entire process from the kernel's memory space. Otherwise, it would kind of lose that status about telling the parent why it ended and what it ended with. So we had to keep it around, which is why it's sitting there taking up a bit of memory. Now, of course, when I run this, it's gone, and it's been cleaned up. If I add another, let's make this down to a sleep 10. If I add another one down here at the end, sleep, let's make it pretty long just so I can catch it. 60, rebuild. So run fork, or pardon me, I can check it, switches to defunct, and then as soon as the timeout expires, the parent process basically collected it by calling wait, and when it called wait, it got rid of that defunct listing here. So now all we're left with is the parent process running, so 07, so 07 was this one. And now when that expires, of course, it'll be removed from the stack there. Or removed, pardon me, from the listing of processes. Okay, so that's the one thing I wanted to show here. I want to now switch gears, and I'm going to show a separate little program I've got written. It's going to show what happens if you call fork repeatedly. So there's sort of this non-intuitive behavior on fork that you get two returns from the same call. So here's a simple program. We're going to loop through, in this case I'm only going through 1 and 2, so a couple times. I'm going to call fork, print out the PID of the process that we kind of returned into, and at the very end I'm going to delay a slight bit and then print out my PID. So your first guess, if you didn't quite understand what fork was going to do for us, you think, well, I'm going to print out my own PID twice, and then I'm going to print out my own PID a third time. Let's prove that's true. Let's get rid of fork. Save that, build, and this is called fork loop. So fork loop. So we print out our own PID twice, and then we finally print it out a third time. Okay, so it gets a little more interesting when we start calling fork. Why? Well, we're going to return from this fork 2 times. Each time through. So wait, what just happened? Well, the first time we went through the loop, we ended up here returning twice. And so we had 74 and 75 were the 2 processes that returned. We then go through the same loop. Well, each came back to the same point. We had duplicated sort of the memory space. So each one had just finished going through on I equals 1. Now each one goes through on I equals 2. So each one calls fork again. So I get 4 calls on the second pass. So I now have 4 processes returned from this fork. 2 multiplied by 2, we got 4 now. And then at the very end, I have a slight delay, and then each one prints out their own PID at the end. So here are the 4 that ended. So now you can start thinking, well, what's going to happen if I switch this to 4? Each time through, we double the number of processes. We started with 1, so we end up with 2 to the 4th. So I can do make and fork loop. So we go through here. Now I'm not calling wait on any of them, so they're all just kind of gonna die when they do. And we can see here that in fact the main one left and we returned back to the command line and it printed this out in the middle. But if we were to count these, we'd see that there are 16 lines here. We ended up having 16 processes that ended just by putting my fork in a loop. So we want to be very careful about how we do this. And a final note on this, there's a while one fork. This has a special name. Oops, let me get rid of that. I can comment out all this code up here. This is a fork bomb. So a fork bomb will simply continuously fork every time through, launching another process. Now I'm not actually going to run that because I really don't want to try and clean up a fork bomb off my system. The current Linux kernels are going to limit the number of processes that can begin generating, but this is going to be set up that would have run in a loop, and so I'd have to go through and kill a bunch of processes. Okay, so that concludes the demo here on fork. What did we talk about? Well, we first learned that fork is a function call that spawns a new process. It duplicates the memory space of the current process, and it returns twice. So you basically come in returning to the parent process and returning into the child process. We saw that we could check if there was an error by checking for PID less than 0. If it is 0, we knew that we were the child, and otherwise we saw that it was greater than that, we must be the parent. We saw that we could do some work in each of the child and the parent, and how we could work between those. And then we really talked about how we could use wait, how it would clean up zombie processes and help free some memory from that. And we saw that we could sort of get information from the child back to the parent through that return statement. Yeah, well, thank you very much for watching.